Hello and welcome to the second of the videos, The Mantle is Not Molten and Other Stories. This time we're going to look at a little bit of convection correction. First of all, let's touch base a little bit with some of the foundations that we set in the last video. This concept of powerful knowledge that Lambert is saying is made by specialist communities or disciplines made in accordance with rigorous and demanding procedures. It's designed there to test knowledge and claims potentially to destruction. These state-of-the-art epistemic practices are established to ensure that the knowledge created is reliable and truthful indeed, that it is the best that it can be. And Young goes on to look at some of the things that this knowledge enables. It's powerful because it provides the best understanding of the natural worlds that we experience. It enables you to envisage alternatives, and it enables you to question it and the authority on which it is based. And I think we're going to meet all of these as we continue in our journey. Remember this quotation by Konrad Lorenz where he says, truth in science, we're pursuing this truth here, can be defined as the working hypothesis best suited to open the way for the next and better one. So that's really what we're looking for. And remember, we keep touching base with this schema just to help make sure that we're grasping the key points as we move forward. We're noticing that we have this expanding evidence base, which is leading to an evolving theory. Last video, we looked at the continental evidence that Wegener saw continental drift. Convection currents is first proposed by Arthur Holmes, then the seafloor evidence that led ultimately to the concept of seafloor spreading, and Harry Hess picking up again that notion of convection currents. And this was the model that he came up with. And this is the model that looks remarkably similar to the kinds of neat convection cells that we'll get in the Google image search we do for plate tectonic convection. But what we're going to discover today is that very, very soon after Hess proposed this, it was already being tweaked and changed. Because we only need to move forward to 1967 to a very important and seminal paper by Dan Mackenzie, where he took this aspects of the theory of plate tectonics that had been developed and emerging at that point and applied them to the sphere, not the two-dimensional world or diagram like this, but into the three-dimensional sphere of the reality of what's going on. Now, I don't mind admitting that the mathematics in Mackenzie's paper is way, way, way beyond me. And he was producing diagrams like this that allowed him to kind of visualize in this complex three-dimensional manner the way in which these different plates move in relation to each other. But one thing is very clear. When he gets towards the end, he says this: the North Pacific shows the remarkable success of what he called paving stone theory in an alternative universe. This is the name given to plate tectonics. That was the name that he gave. It didn't catch on. Plate tectonics did. But that's what he means. This plate tectonics theory, or paving stone theory, was successful over a quarter of the Earth's surface, and he expected it to apply to the other three. But there was a problem. The problem lay in the nature of the mechanism driving it. And he, having done this three-dimensional analysis, said it's difficult to believe that the convection cells which drive the motion are actually closely related to the boundaries of the plates. This is what Hess was suggesting. The rising of the convection here, the rising limb is under the ridge and the falling limb is under the trench. And what Mackenzie is saying from his 3D analysis is it's actually very hard to picture this. So, goodbye to those neat little convection cells. Hello to another really important paper by Walter AlSasser in 1971. Even before we look at anything else, let's look at this title: Sea Floor Spreading as Thermal Convection. Now remember, what Hess had suggested was that the active driving element of the whole process was these convection currents in the mantle. The plates simply rode on top as passive passengers. But what AlSasser is suggesting and hinting, even in the title, is that this process of seafloor spreading that is occurring in the lithospheric plates is actually part of the convection. Now, just before we look at his paper in detail, let's take a few moments to consider a good and detailed understanding of what we mean by convection. In a popular sense, if I asked you to define convection, I wonder what you would say. Again, if you go to do a Google image search, you'll see lots of things like this. And you maybe thought of something like this. Convection is the rising of hot liquid or gas as has been heated from below. It rises, eventually cools, and sinks back down again, and you get these lovely little convection cells. But almost every diagram that you will see on the internet for convection looks like this, with heating from below. But if we go into the world of physics and define it slightly more precisely, we discover that there's a little bit more to say about convection than that. Convection is, first of all, a buoyancy-driven flow. So, actual fact, what we're dealing with here in the first instance is this notion of buoyancy, whether something will rise or fall, but it is resulting from density differences. It occurs in a medium that can flow. So it's the density differences that will give something a positive buoyancy and it will float or rise, or a negative buoyancy and it will sink. It's not in the first instance the temperature. It's the temperature creates these density differences that then cause the convection. Rising of less dense material, sinking of more dense material. Just for completeness sake, this has got to occur in a gravitational field, but we'll not be dealing with that here. Right, here's convection in our ordinary sense. It's the hot material has been heated, it expands and rises. Or colder material cools and contracts and has a greater density and therefore sinks. Which tells us that convection can result from heating from below. Something is heated, it expands, becomes less dense and rises. Or convection can occur from cooling from above. Something cools, is more dense, and it sinks. And according to our definition of convection here, both of these are part of a convection. The rising of the hot material and the sinking of the cold material. Both of these are buoyancy-driven flows resulting from density differences. It may be heated from below and rise, but equally it may be cooled from above and sink. Let's take a look at an example of that. If a submarine wants to sink, it pumps water into its tanks, its density increases, and it dives. If it wants to come back up to the surface again, it pumps that water out, and up it comes to the surface. This is actually quite a good illustration because it's nothing to do with temperature at all. It's to do simply with the density differences. Either an increase in density giving it a negative buoyancy and it will sink, or a decrease in density, here we go, giving it a positive buoyancy and it will rise. Here's another little example. This is a fabulous volcano. This is Erta Ali in the East African Rift Valley, the Danakil Depression in Ethiopia, the hottest place, or one of the hottest places on our planet, not just because of the volcanoes. But Erta Ali is one of the few volcanoes across the world that actually has a semi-permanent lava lake in the crater. And this is going to give us a good opportunity to explore some of this convection and the differences in density. And I'm going to get you to look first of all up here towards the top right of the GIF. I want you to look here particularly at this bit of the crust here, the bit of the layer in the top. That lava, which is molten, cools due to contact from the air and creates this skin or this layer on the top of it, kind of like a skin on a custard. But because it is cooled, it contracts a little bit, and because it contracts a little bit, it's got greater density. And can you see what's happening here? Can you see that slab of cooled lava on the top sinking back down again because it has got greater density than the hotter lava below? And here we have a brilliant example of cooling from above helping drive the convection. Now let's take a look over at the left here, because as this moves apart, what you're getting is tension in this bit of the block, and it splits apart, and you can see the hot material welling up here underneath. Watch when it splits apart, gives an opportunity for this hotter material. Look at it go up. You can see it immediately like it's breathing out, where you get this opportunity. The hotter material will rise to fill the gap that is created there. But this actually is a great example of that heating or that cooling from above, which helps to drive the convection. So with that in mind, let's come back into our definition, the buoyancy-driven flow resulting from differences in density, and back into AlSasser's paper. He says this: some authors have presumed that convection motions in the upper mantle are caused primarily by heating from below, but there's no evidence for this, he says. The cold lithosphere goes down at a slant that is usually below the continent, and we do have evidence for that, not only the trench, but also the earthquakes along the Wadati-Benioff zone. And he then says this: what this amounts to is a sort of upside-down convection, in which motion is engendered, created by a cold top layer sinking, rather than a hot bottom layer rising. Most of the convection generating forces, he says, are exerted by parts of the oceanic lithosphere that have been cooled at the free surface, he says. And this relatively cold material sinks down and hereby serves as the primary driving agency of this circulation. The convection actually is driven by cooling from above. As the material sinks, it will create a potentially vacant region in the lithospheric plate, but the vacancy will not really arise. Material flowing horizontally will exhibit tensile strains and stresses. To try and illustrate that a little bit, here he has this notion of the cold, old, dense lithospheric plate subducting down into the asthenosphere. And as it does so, it will create a tension over at this location here, which could, you might think, cause a gap. But no, he says it's going to thin the plate out here and going to cause that tension. And that is actually what allows the material below to convect up, to upwell up. But this is a passive convection in response to the thinning of the plates. The main driver here is the sinking of the cold old slab down. This GIF might help explain that a little bit. You can see here the tension and the upwelling of the mantle material below. And as that mantle material upwells below, it brings the heat closer to the surface, giving a positive buoyancy to the plate here, causing it to rise up and form the ridge. And because of the decompression melting of the mantle material to produce magma, that helps to create new seafloor, which is young, hot and high, and therefore that gives the ridge. That submarine ridges are dominated by this tension he talks about is noted. It is nearly impossible, though, he says, to conceive of a curtain of hot material rising and pushing the lithosphere apart. Now, this is back again to that neat convection cell that Hess had suggested, that the ridges are the places where you get these curtains of mantle material rising up by convection. What AlSasser is suggesting is this: given that we have these transform faults that are found all along the constructive plate margins where the plates are moving apart. In effect, what you would need to have is a convection cell rising here and also one rising over here. So these two completely different separate cells, or do they have this kind of weird sudden 90-degree bend followed by another 90-degree bend? And AlSasser is basically saying we've no evidence that convection would operate in something like this. So if it's convection that is causing the surface plate's manifestations, how do you explain the convection being in that pattern? AlSasser is suggesting it's not easy. However, if we go on to say that the upwelling here of the hotter mantle material is responding to what is happening in the plates, if the plates, and particularly what's happening at this margin here, are the active part of the system and the main drivers of the system, then it's no surprise that what's happening in the mantle below will reflect what the plates above are doing. The upwelling is a passive upwelling in the upper mantle in response to the thinning of the plates above by these tension forces. But because what the mantle does is reflect what the plates are doing, then what's happening down below is not at all unusual. Now, I went on to look at a series of other pieces of evidence, but I've just given you a flavour of a few bits there. This is as he comes towards his conclusion. Now, though one can feel sure that the current interpretation so far is the loss of material from the lithosphere near the trenches where it subducts down, and the gain of material in the middle of the ridges where the new material passively upwells to create the new crust. We can be sure of that, he says. The detailed mechanisms are still very obscure. Of course, this is 1971. There's still a lot to discover. But even then, in 1971, there seems to be general agreement on one point. The descending slab is being pulled by its own gravity, it being colder than its surroundings at all levels. So the key point to note here is that neat convection cell model that Harry Hess had put forward had already largely been rejected by the late 60s, early 70s. The evidence was suggesting that in actual fact, the plates are part of that convection process. So let's summarize the two models in this GIF. This is basically the kinds of things that Arthur Holmes and Harry Hess suggested, that the main driver of plates is the convection current in the mantle. The plates are merely the passengers that are riding passively on top of that. Our actual understanding of what is actually happening, at least our model of what's happening, is much more represented by this. It's a gravity-driven, density-driven model, where the plate is actually the active component. It is sinking at subduction zones where the cold, old, dense plate is now dense enough and has a negative buoyancy and will sink into the asthenosphere, which is solid but ductile. The ridge, which is young, hot and high, the material there that's created will slide off the edge of the ridge. So you're going from a gravitational height at the ridge to a gravitational trough or depth at the trench. And it's that gravitational drive of the differences in density causing the negative buoyancy that will make it sink that is causing the plates movement. The plates are part of the convection system. And in actual fact, in this model, the movement of the mantle, or the asthenosphere below, is induced by the movements in the plates in very large part. It's kind of like if you take a paddle in a canoe and move it through the water. The water will move because the paddle is going through the water. It's induced by the paddle. And this is part of that big mental shift that we have to make. And again, just to stress, this is going on in the early 1970s. This is a fabulous book by Roy Livermore. The tectonic plates are moving. A wonderful writing style, well worth checking out. But he summarises the main points from this revised theory as put forward by AlSasser. But particular importance are points 5, convection is driven not by heating from below but cooling from above. And 6, the primary driving forces for convection are exerted by the slabs of lithosphere sinking along the Wadati-Benioff zones. So back to our schema. We have our expanding evidence base, continental evidence, first of all, with Wegener and the continental drift. The convection currents is initially proposed by Holmes. The seafloor evidence that came out, which led to the idea of seafloor spreading, and Hess reviving those neat little convection cells and tweaking them on the basis of the evidence. But what we discover is that in its first form, in the late 60s, early 70s, that plate tectonics as a theory saw convection like this. Convection includes the plates. Convection is mostly driven by the plates, which is a very, very different understanding than the common one today, isn't it? Roy Livermore goes on to write this. He says, some of Holmes' revolutionary ideas, notion for creation, were revived by Hess in the 50s, as we saw, rebranded to seafloor spreading, as we saw. And this, he quotes from Hess. We've already heard him say this, that mid-ocean ridges are interpreted as representing the rising limbs of Mantle convection cells. And he followed Holmes by believing that the continents rise passively on the convecting mantle. Now, Livermore goes on to say, somehow these two ideas, brilliant as they were when they were advanced by Holmes in the 30s, and this was wonderful hypothesizing. It was doing science. There's nothing wrong with this. But they were superseded, and that's called doing science too. The problem is that these two ideas, brilliant as they were when they were advanced, like tuberculosis, Livermore says, have persisted despite half a century of scientific progress. In fact, they were already superseded in the late 60s. In particular, here you can see saying the volcanism at the ridge results not from the rising convection currents, and moreover that the plates are able to drive themselves. Like tuberculosis, they have persisted. Or, to come back to my analogy, they're zombie ideas that, despite having died out in the early 1970s, are still roaming the pages of geography textbooks and the internet search results of Google. But it's time for these zombies to be slayed. Now, at this point, we're going to take a short excursus as to why this is the case. We're moving out of science, I suppose, into psychology here. And this is just something that I've been interested to try and understand. Why is it that these ideas have hung on as long as they might? And for this, I'm going to lean into a wonderful book by Jeffrey Davies I've been reading this summer. And this is what he says on this matter. He says there's a colonizer effect in scientific ideas, analogous to the colonizer effect in island ecosystems. The first organisms to reach the new island by whatever chance circumstances bring them there are free to establish themselves. But later organisms have to compete with those who are already there. The result is that even much later, island ecosystems tend to be dominated by the species that arrived first. Now, when a new scientific field is opened up, he says, and the ideas first proposed about how it works, they tend to become the benchmark. And later ideas have to compete to establish themselves. This is an example of a more general quirk of the alleged intelligence of human beings, according to Daniel Kahneman in his book Thinking Fast and Slow, another fabulous book. When we encounter something new, we tend to assume our first experience of it is normal, and that any change from that state is an aberration, even though we might by chance have encountered it in an atypical state. Now, you might be experiencing this through this video. This might be challenging some deeply held or strongly held views that have just been there for pretty much all of your geography education. You might be struggling a little bit with the, hold on a minute, has everything that I've been told so far a lie? Well, no. It's not. It is part of this story. This was part of where the theory had arrived by the late 60s. It's just that's not where the theory had stopped. We have moved on. And I just think that it's worthwhile for us as geography teachers to move on as well. Davies includes this diagram in his book, diagram from a paper by Isaacs, Oliver and Sykes in 1968, and he says this about it. So it was with this diagram. The authors included features that already had a history and some reasonable evidence behind them, as we'll see later. There's truth in this diagram. You might look at it and go, yeah, that seems pretty reasonable. I could use that with my classes. However, he says there was no compelling reason to draw a black line along the bottom and thus confine motions related to the moving plates strictly to the shallower or upper mantle. Nor did the arrows of the return flow under the plates need to be so shallow. They were not based on any fluid dynamic insight or any quantitative demonstration. There was no evidence for them. The arrows were just drawn on. Some other features were also schematic. In other words, they were kind of done in a very, very simplified manner, almost like a cartoon. They would need to be refined. Of course they would. Whereas before, there were general ideas and some debate about the strength of the mantle, both shallow and deep. Once this diagram was published, etched in simple, bold lines, the picture was firmly placed in many minds, and it became harder to think and talk in any other way. It took root, this colonizer, and was hard to get rid of. All of that to say that as we approach this, we don't approach this with a blank slate. We approach this already with conceptions, misconceptions perhaps, zombie ideas. And there's an interesting pedagogical point in this, because whenever we teach our pupils this, it's highly likely that they'll not come at this as a blank slate. So it's highly likely that there'll be some zombies that they will have to slay in order to understand the proper way of how plate tectonics seems to work. And on that subject, I'm going to share with you now a few points of autobiographical interest in terms of my own personal journey towards this. In order for me to fully come to terms with this newer and better and more accurate model of plate tectonics, there were a few ideas that I needed to displace, a few zombies that needed to be slayed. The first of them is this, that there are large neat convection cells in the mantle. So many Google image searches will show you that. No, they're not. Convection does occur, but it includes the plates. The second zombie idea is that plates are driven mainly by the mantle convection currents. No, they're not. Convection is mainly driven by the plates. It's the plates that are the active component. Convection is driven mainly by rising hot mantle rock. No, convection is driven mainly by the sinking of cold plates. This is cooling from above, increasing the density, causing the cool things to sink. Now, it may be worthwhile you reflecting for yourself in light of what you've heard here. Are there any zombie ideas not listed there that perhaps you need to slay? Take a little bit of time to think what they might be and what are the better ideas that might replace those. So let's see if we can pull that understanding together in a neat little diagrammatic form. What we're looking at here is some of the plates. I'll just turn my pointer on here. So these are the lithospheric plates here. Down beneath that we've got the asthenosphere, and down below here we've got the mantle transition zone. And what is happening here is that the cold, old, dense lithospheric plate is sinking down, is subducting into the asthenosphere below, which is solid but ductile, so will flow. And that is one of the main drivers of plate motion, the slab pull. As it sinks down, the stress is transferred back up into the plate above, which causes it to be pulled along as well. And that's that slab pulling force that pulls it down into the mantle. The mantle does flow, the asthenosphere does flow, but these currents here are as much induced by the sinking of the slab as anything else. These are induced, these are passive. The active component here is the slab that is sinking down. Now, as that sinks down, it doesn't melt. It doesn't get incorporated back into the mantle. Hence the term destructive plate margin that we seem to use in geography is probably not the best one to use. We have evidence that these slabs, once they come down to the mantle transition zone, they make their way right down to the core mantle boundary. Now, down here they may well start to break up and deform in the denser mantle material below, but there is evidence here that many of them will come to this core mantle boundary and gather in these slab graveyards down at the core mantle boundary itself. But that pulling force, of course, is going to create a tension over here, and that tension itself is going to thin the plate, and that is going to cause a passive upwelling. So there is convectional rising here, but it's convectional rising that's caused by the plate. The plate is the active component here. And as that rises up, it comes from just the upper mantle here, bringing the hotter material towards the surface. And because the hotter material is brought towards the surface, that area is heated a little bit. It expands and it gives it a positive buoyancy. And the new material that's coming up here, the magma that's coming in to create the new plate here, is also young and hot and therefore high. That's what gives it this positive buoyancy. But as it cools, it will slide down off the side of the ridge, pushing the plates apart. So you have this slab pull, which is driven by the cooling from above, increasing the density of this rock, causing it to sink down. That creates the tension there, thinning the plate, allowing the mantle material to passively upwell, creating this ridge from which the material slides off, and it's the slab pull. And that is the essence of the new understanding. That is highly simplified down to this model form. But this is basically the model that I teach to my sixth formers. And I teach a version of it as well to Key Stage 4, which we'll take a look at maybe in the next video. But that is the essence of it. Now, just one final thing to add on here, and that is mantle plumes. We're not really going to talk about them much in this video, other than just to acknowledge that they exist. There is evidence that these mantle plumes exist, although their nature and how they're formed is still up for debate and discussion. But the surface manifestation of the hotspots are explained by these mantle plumes, and we're seeing some evidence from scans of the interior of the Earth that they exist. Now, the mantle plumes are convectional rising, and this is from heating from below. So this is heat from the core that's escaping out and is coming up through the mantle here. That is a rising, it's a positive buoyancy, so it is a heating from below rising, but they don't rise up in curtains of neat convection cells that correspond and counteract these sheets of the slabs coming down. These are narrow conduits that are rising up. And in fact, it seems that they are separate from the cold slab sinking down. It seems like a separate convectional process. Although we are beginning to explore how they might interact. There is some geochemical evidence from the volcanic material and rock at some of the hot spots of some material that has been brought down all the way down to the bottom of the core mantle boundary. Hundreds of millions of years it takes for that to happen, and for then rise up again here, perhaps 500 million years later, to be erupted at the surface. There does seem to be some kind of interaction down below between these. The full nature of it is not really understood as yet. We don't really know. But that's a narrow conduit, which has nothing to do with this particular model of how plates move. This is slab pull and ridge push are the main drivers, but just because those are part of the mantle dynamics is worth mentioning. So we can take that and turn it into a diagram like this. This is a diagram that I use with my sixth formers. And you will see here from this that it does represent in cartoon form and schema form the various bits that I've just shown you here. We've got this slab pull force operating here, slab pull here, creating the tension, the passive upwelling in the upper asthenosphere, giving us our ridge push and the mantle plume. Now, I have found as I've taught this that this is no more difficult to teach than the previous model of the neat convection cells. Once you help the students to set aside the zombies, this actually is relatively easy for them to grasp. Let's watch a wee bit of this video, which reflects a little bit of some of these mantle plumes that are rising up that our scans of the interior of the Earth have shown to us. And you'll see that this is a much, much more chaotic form. You've two very, very large regions there where it rises up. Those are large, low shear velocity provinces. Those are very, very mysterious. We don't really know what they are. One below Africa, one below the Pacific Ocean. But you can see all of these different chaotic blobs rising up. They're certainly not aligned with the plates, margins, and they're certainly not rising up in curtains like that. This is a better and more accurate understanding of what's going on. Okay, let me quote a few more contemporary writers on this. David Berkovici says this: "The link between plate tectonics and mantle convection is one of the oldest and most challenging problems in the history of geodynamics. The original theories of mantle convection put forward by Holmes were developed in the context of explaining continental drift as articulated by Wegener. Mantle convection is widely accepted to be the engine for plate motion, since it's a fundamental mechanism for exploiting the energy sources of the Earth's interior. But it is now generally regarded that the plates themselves are a feature of convection, in that they are the mobile upper thermal They are the mobile upper thermal boundary layer of the convection cells that thicken as they cool in their migration away from the ridges until the plates are heavy enough to sink along subduction zones." Pete Loader says this: "It's now generally accepted that plates in the mantle are a single coupled system, with plates moving by slab pull, which helps to drive mantle convection patterns rather than the other way round. In this way, the plates can be viewed as part of the overall convection system, and not simply as mere passengers rising above the convecting mantle. Therefore, it is correct to say that convection currents move the plates, provided that it is understood that the plates are part of the mantle and therefore form an essential part of the mantle convection system." So back to our schema. Our expanding evidence base and our evolving theory has taken us all the way from continental drift via Holmes convection, through to the seafloor evidence and seafloor spreading, and Hess's convection, through to the understanding that evolved in the early 70s, late 60s, that convection actually includes the plates and is mostly driven by the plates. The end. Or is it? Well, you were expecting that, weren't you? Because I've taken you up to the 1970s. There have been 50 years since then. And if the science of plate tectonics evolved over the period of time from Wegener to when it finally crystallized in the 1960s, if it evolved then, surely it has evolved since then. And indeed it has. Now, not to the same degree. There was a massive paradigm shift in the late 60s, early 70s that totally changed the way that we saw and understood how the world as a system operated. We haven't had anything close to that paradigm shift, but we certainly have had a significant continuing evolution of our ideas and our understandings of exactly how slab pull and ridge push operate. Because what we've been able to do is take a journey to the centre of the Earth. Well, not literally, of course, we can't travel down there, but we have developed some techniques that allow us to peer in underneath to see what lies beneath. They're techniques known as seismic tomography, and they're beginning to open our eyes to what exactly is going on down there. So our final video, we're going to take a field trip to the centre of the Earth.